Good morning. In this lecture, we will discuss about Monte Carlo simulation. Monte Carlo simulation is a powerful technique to solve the complex problems using simulation method. So basically, Monte Carlo simulation is a computerized mathematical technique to generate random samples based on some known distribution for numerical experiments. So this figure shows how the Monte Carlo simulation works. So let's say we have a stochastic model and there are three inputs x1, x2 and x3, and these inputs are basically random variable. So these inputs are random variable. So to basically calculate this model, we need these three random variable and we simulate x1, x2, x3 from the given distribution. And once we simulate this value, this go into this model and then finally we get the output y. So let us discuss little bit more about this Monte Carlo simulation. The model that we're discussing, this is the model we have, and this requires three input x1, x2 and x3. All are random variable. So let's say x1 follows some normal distribution. It can be having any other kind of distribution also. It can be exponential distribution, gamma distribution, bival distribution. So with the given distribution, we can simulate one value of x1. Similarly, x2 will follow some other distribution and we can simulate one value for x2. Similarly, we can do for x3. So in this way, we will have one set of x1, x2 and x3. These are the input. So we will put this into the model and we can get the output y value. Similarly, we can basically perform this many times. So we can have another set of x1, x2, x3, another set of x1, x2, x3. So this means we are doing this a large number of iterations. So we will have in each case y1, y2, yn, ym and yn. So these are the possible outcome we will have. Some of the outcome may be same and some of the outcome may be different. So basically in that case we can plot a histogram, and this histogram will give me the inference about the result. So basically this Monte Carlo method is used by the professionals in various disciplines. For example, this is used in finance, project management, energy, manufacturing industry, engineering, research and development, and insurance company also uses such kind of simulation technique. Transportation as well as oil and gas companies uses this kind of Monte Carlo simulation method to solve their complex problems. This method was first used by the scientists working on a project, that is basically a Manhattan project, for making atom bomb in 1940 during Second World War. So this method can be used in those situations where we need to make an estimate and uncertain decision, such as whether forecast prediction or a stock market. So where we have uncertainty, this kind of method is often used for simulating and giving the result, giving the predictions in the future. So what is the basic idea of Monte Carlo simulation? So basically the basic idea can be summarized like this. Each random variable, so we have some inputs, these inputs are treated as a random variable. So each random variable in the problem is sampled several times, maybe 1,000 times, 10,000 times, even more than that, and this represents real distribution. So if I increase the number of sample, it will converge towards the real distribution. So we are randomly sampling. Each realization of all the random variables in the problem produces one realization of the problem itself. So for example, in the previous case, if we simulate x1, x2, x3, this is one realization. Next time, if we simulate x1, x2, x3, let's call this the first iteration, and this is the second iteration. So this is the second realization. Similarly, we can have nth realization, x1, x2, and x3. So this is the nth realization of x1, x2, x3. So the problem is solved deterministically for each realization known as simulation cycle or trial or run. So what we are doing is, for each set of this x1, x2, x3, we can solve the problem deterministically. So this means what we are doing is, we have this model and then we plug this x1, x2, x3, that will give me a deterministic solution for a particular set of x1, x2, x3 using this model. So we can summarize the Monte-Carlo simulation in 5 steps. So what are these steps? So first step, to draw the random samples. So we have to draw a random sample for each random variable from its underlying statistical distribution. So we know the distribution, we have to draw the random sample. That is the first step. Second step, that is to evaluate the model deterministically. So whatever we sample have, we can use this data or this sample to evaluate the model, and in this case we are using a deterministic approach to calculate the output y. Now in the next step, we have to store all the results or that is coming from the model, or we may need to count these results sometime also. So either we have to store or we have to count these results that is coming from the deterministic model. In the next step, we have to basically repeat a step 1, 2, 3 n number of times. N is basically number of simulation. So we have to repeat these steps. So we have to draw, evaluate, and store. So many times if we do this process, then finally we have to go into the 5th step, that is analysis of the result. So based upon this result, we can plot the histogram, we can calculate summary statistics, for example mean, median, variance. We can also calculate confidence interval on 95% interval, 99% interval. So these are the 5 steps that is used in Monte-Carlo simulation. Now if you see this Monte-Carlo simulation, the step 2, basically evaluation in a model. So a step 2 shows Monte-Carlo simulation is applied to a model. Now this model can be a mathematical function, logical function, or something like fault tree, or it can be a computational model. So a large variety of model can be covered using a Monte-Carlo simulation. Another important point, we must have appropriate probability distribution for each of the uncertain input parameters. So for example, in this case we have x1, x2, x3. We must know how the x1 varies. What is the particular distribution for x1? What is the particular distribution for x2? Similarly, for each input variable, we must know what is the corresponding distribution. So for each random variable, we should know what is the corresponding distribution. And this is particularly important because our result depends upon what choice of distribution we are making. So the choice of probability distribution is fundamentally important because it has a direct impact on the calculated outcome. So if you take different distribution, you will come across different results. So what is the best distribution that can describe your input, that is particularly important. So you must have to take a distribution that clearly shows the input follow that pattern. Now this Monte-Carlo simulation we will discuss using an example, and this example we also discussed in the previous class, that is called calculation of profit in terms of income and expenses. So let us discuss this exercise. So this exercise says, let's say we have income for some company I and expenses, that is E. So profit can be given as, let's call this as a R. It can be given as income minus expenses, where R is the total profit for the year, I is the income, and E represents the expenses. Now let us make some assumption. Assuming income can be described by a normal distribution with mean of this quantity and variance of this quantity. Similarly, expenses can be modeled using exponential distribution with lambda value given like this. So you see, we said earlier, the input variable will be described by a distribution. In this case, one variable, that income, that is my random variable, this is described by a normal distribution, and expenses, that is another random variable, and this is described by a exponential distribution. Now the first task is plot the density function for the income and expenses. So we want to plot first, let's say, how this income and expenses looks like, and we know the probability distribution because income is basically normally distributed. So this income follows a normal distribution and with mean of 60,000 and a standard deviation of 8,000. So let us plot this using an Excel sheet. So let's plot, let's call this as a serial number 1, or let's say X value. So on this here we will have X value. So we want to plot, so this is on the X axis we will have X value. So X value can be income or it can be expenses. So you see on the X axis we will plot income, or we can also plot expenses. So let's start with 0 and increment of 1000, and then we can basically drag this. So let's go, because mean is 60,000 and the standard deviation is, so we need to go a little bit higher side. So this is 82,000, let's take up to 101. So this is around 99,000. So let's say first calculate normal PDF. So this is normal PDF. So in Excel we have a function non-dist. So this gives me the function, then I have to press tab key, and then it is asking X value. So let's say X value is this, and we know mean is 60,000 and a standard deviation is 8,000, and it is asking, do you want cumulative or probability mass function? Let's plot probability mass function, and then I have to press enter key. So this is giving me normal PDF when X is equals to 0. I can drag this. So this is giving me normal PDF for different value of X. Now let us plot this value. We can also find, let us first plot and then we can discuss. So let's say go up to 100. So here we can go insert, plot. So this is the function, and then I can basically, this graph is going from, so I have to change up to 101 because we have all this data here. So this is my function we have, and we can also change the x-axis. So let's first plot exponential, and then we can basically find. So let's say exponential PDF. So to calculate the exponential PDF, once again we will go and put this function exponential distribution expo.dist and then press tab key, and then it is asking me the x value and the corresponding lambda. So if you remember, in this case we know lambda is given and 6.25 into 10 to the power minus 5. So we have to put this value 6.25 into 10 raised to the power minus 5. And then we have to also put false because this is a PDF. So this is giving me the exponential PDF. Now we have to double click here, and this will give me the value of PDF corresponding to all values of x. Now let us plot on the same graph exponential PDF. So select data, and then we have to add, and let us call this series as exponential PDF, exponential PDF, and then value will have, this will go from here to 101, and then we have to press OK. So this is the exponential PDF. So this value should go up to 101. So I think I have to drag this. So let's drag this. So this is the exponential PDF. Now we can also change the x-axis. So x-axis can be either income or it can be expenses. So let's change the x-axis. So series 1, I have to edit x-axis. So x-axis is from 0 to 101. Similarly, for exponential again, I have to check the x. So this is series 1 is basically your normal case, and this exponential PDF. So now we can see this is the x-axis, which can be either income or expenses. So this can be income or it can be expenses. And this side we have the PDF. So now you see this is, so the normal distribution, that is my income, and this is expenses. So basically using this graph we can see what kind of distribution random variable I follows and what kind of distribution and how it looks like when we plot on the x-axis. Sometimes you see in this region we have income is high, but in this region we have expenses that is higher. So basically we have to calculate the total profit by subtracting these two variables. So let us do the other part of this problem. So this is the first part that says we have to plot the random variable for the income and expenses. Next part says construct the histogram and compute the sample statistics for total profit R using Monte-Carlo simulation. So now it is saying we have to use Monte-Carlo simulation and plot the histogram using Monte-Carlo simulation, and it says we have to use 100 trials. So this means I have to simulate 100 samples of income and 100 samples of expenses, and then we have to calculate profit, and then we have to plot the histogram. So let's do this using the Excel sheet. So let's say here we have this side we will plot income and this side we will have expenses. So income parameter says mean is 60,000, standard deviation is 8,000, and then we have to use Monte Carlo simulation to generate samples. So let us first generate uniform random variable between 0 and 1. In Excel we have a rand function that can be used to generate random variable. So this is equals to RAND. So let's generate a random number. So this is giving me a random number between 0 and 1. So let's calculate 100 such random numbers. So we can go up to, so what is the first cell? So this will start at 11. So we have to go up to 110. So this is the 100 numbers of sample we will have. So 100 trials. Now this is the first step of Monte Carlo simulation. Says we have to basically simulate samples from normal distribution and corresponding mean and standard deviation is given. So what we will do is we have this random numbers between 0 and 1, and we will do inverse. If you remember this, we discussed earlier classes also. Now we will do inverse of this cumulative CDF, and correspondingly we can get the income value. So let's do this inversion. So we will use inverse CDF method, and Excel has a function norm inverse. So norm inverse, and this asks me, so we have to put tab key here, and then this is asking me corresponding probability. So this is the corresponding probability, and what is the mean of that distribution? So this is the mean, and what is the standard deviation? So this is the standard deviation we have, and then we can put here the dollar sign to fix this cell mean and variance. So now these cells are fixed. So I think I have done a mistake. This is not required. So this is the corresponding, so we simulated one income value, that followed normal distribution. So first we simulated a random variable and corresponding random variable using this mean and a standard deviation. Basically we simulated a random sample for income. Similarly I can drag this and we can simulate 100 samples of incomes. Similarly now we have to estimate, or we have to basically simulate 100 samples for corresponding expenses, that is follows the exponential distribution. Before that we can also calculate, we have basically sampled this, we can calculate sample mean. So let's calculate average function. So this is equals to average, this goes from this to 110. So this goes up to 110, yeah. So this will give me corresponding mean. You see the original mean is 60,000 and sample mean is around 59,680. Correspondingly we can calculate a standard deviation. So there is a function, a standard deviation, and we have to give range, and this goes from this to 110. So this is the corresponding standard deviation. So you see the sample standard deviation is different than the actual or true distribution, that is true standard deviation. If I increase my sample size, this will reach towards the true population or true sample or true standard deviation in this case you can say. Now let us simulate correspondingly expenses. To simulate expenses, basically that follow exponential distribution, we will derive in this case inverse using inverse function method, we can basically derive an expression for simulating corresponding x-axis. So let us first derive the expression for, in this case. So you see, this is what we have plotted. So this is my income and this is my expenses. So now using this, we can use Excel sheet to perform Monte Carlo simulation. And the first step, we have to draw the sample for each random variable. In the Excel, we use rand function to generate random numbers, and then we used inverse transformation technique for normal distribution, and we will also use same for exponential distribution. If you see, previously we used norm inverse function in Excel to simulate values or excise value for normal distribution. Now we have to solve for xi when we are using exponential distribution, because in case of exponential distribution we know the exact PDF or exact CDF value. So we can use this inversion method, that is, if fxi basically is equals to ui, then I can basically do inversion, that is xi is equals to f inverse ui, and that will give me the basically inverted function. So let's first find out the expression for xi using the inverse transformation technique for exponential distribution. So let's say we have a random number ui, and then I have correspondingly function fxi, and we know for, in this case, for exponential distribution, CDF is given by this formula 1 minus e raised to the power minus lambda xi. So what we can do is we can take that side, so we can write e raised to the power minus lambda xi. This is equals to 1 minus ui. So here we can write, if I take log both sides, so lambda xi, this is equals to simply 1 minus ui, and then this is log of this. And then we can write xi, so this is xi is equals to minus 1 by lambda log of 1 minus ui. So you see, we can use this to simulate xi value. So my xi will be minus log of 1 minus ui divided by lambda. So we will use this formula to simulate basically random numbers from exponential distribution in Excel sheet. So let us use this, because in normal distribution we have a built-up function, because we cannot derive such kind of expression in case of normal distribution, but in case of exponential distribution we can derive an exact formula for xi in terms of random variable ui. So let us do this and estimate or basically simulate random variables for exponential distribution using Excel sheet. So let us first simulate uniform random number. So this is equals to rand, this function is here, and then we have to basically drag this. So this will give me 100 samples of random number. Now as we derive, this formula is inverse. If we do, this is minus of log, so this is log, so we have to use natural logarithm, so in this case this value, and then we have to press tab, and this asks me number, so number is this, and then we have to so this is the number is 1 minus ui, so this is 1 minus ui is this value, and then I have to divide this by lambda, so there is a negative sign, and this divided by lambda. So we already have this lambda value, that is 6.3 into 10 to the power minus 5. If you remember, this value we have for, in this case, lambda value in this problem is given, that is 6.25. If we basically round, so this will be 6.3, or let me write this value is equals to this, and let us freeze this cell G6. I can put a dollar sign before and after Z. So this is a random number coming from exponential distribution, and this is minus of ln ui, 1 minus ui divided by lambda. So this is what we derived earlier, so you can confirm yourself. So this value is, so minus of ln 1 minus ui divided by lambda. So we can basically drag this value to generate other samples. Now once I have normally distributed income and normally distributed expenses, we can calculate total profit, that is R, that is equals to I minus E. So this is equals to I, income minus expenses. So this will give me the total profit, and then we have to drag this. So now we have calculated profit in each case. So let me check again. So this is income minus expenses. Once again, income minus expenses. Yeah. So now the next part of the question says we have to basically draw the histogram in this case. For this case, we can also calculate sample mean because we have simulated the sample. So let's calculate average, and this is equals to, so we have to give the data. This is for exponential distribution. So I have to take this here, and this will go up to 110. So this is the corresponding sample mean. So now see, the exact mean is 16,000. My sample mean is 17,000 or around 18,000. We can also calculate lambda, that is 1 by sample mean. So this is the sample mean we have. So that is basically 6.9 times 10 to the power minus 5. So this is the sample lambda, and this is the actual lambda we have. Now we have to plot the histogram for the profit. So let's try to plot the histogram. And let's take 20 beans and we can plot this. Let's first find what is the minimum value in all this. So all the simulated sample, what is the minimum value? So let's plot. Let's first find minimum value. So minimum of this, and this goes up to 110. So this is minimum value. Similarly, we can find what is the maximum value. So this number, and this goes up to 110. So this gives me minimum value, and this gives me the maximum value. So we can basically find what is the total range. So that is minimum minus maximum. So that is maximum minus minimum value. So this gives me the range, and then we can find what is the bean interval. So range divided by number of beans. So this is the range, and this divided by number of beans. So this is the bean interval. So in each bean, the interval size is this. So let us find what is the lower bean and what is the upper bean limit. So lower bean limit, we can start with the lower limit. So minimum value, and because we have to iterate this, so we will basically take this iteration number, it's here 1 and then minus 1. You will understand what I am doing here. Minus 1 times this interval. So this will give me the lower bin. So that is, let me freeze this cell, that this cell L6 is freezed. So I have to put a dollar sign. So this is the lower bin size. So we can also find upper bin size. So this is equals to what is the minimum value. So this minimum value we have plus, now this times I don't have to subtract 1 times, and then this value is bin interval. So this will give me this value. So you see, in this case again we have to basically freeze minimum value, that is N5, and we have to also freeze this L. Similarly, let me check here. So this contains N5, so we have to also freeze this N5. So now my first bin is from minus 40,746 to 34,000 with a negative sign 991. So similarly, we can basically find all the lower bin and all the upper bin. So we don't have to go into so much. So basically we can go up to, let's say, we can go up to maximum. So what is the maximum value? So 69,000, so around 69,000. So if I go up to here, that is fine. So there is no need to go beyond this value. So we can go up to here, this should be fine. So now let us find how many numbers, what is the frequency in this bin. So we have to use a function count ifs. So this function is here, and then this is asking me criteria range. So this is the range, and this go up to 110, and then we have to give the criteria. So basically I have to freeze this range, and then this goes, and what is the criteria? In this case my criteria is this is greater than equal to lower bin size. So lower bin is here, and then I can give another criteria. So greater than equals to what? So this is greater than equals to this lower bin, and then we have to put the other criteria. So other criteria range, so range is again same. So this goes up to 110, and then we have to give the criteria, and this is less than equals to this lower bin size. This is L11. So this is L11. I have to put a dollar sign first. So let me, this is this, I have to freeze Z, and then we have to put a apparent sign here. So this is K11. So I think this should be okay. So where is the mistake? So count if Z11 to this is okay, and this is Z11, this is less than equals to L11. So this sign is missing. So I think there was a comma, that's why this problem. So this gives me the frequency in this bin range or this bin interval. Now I can basically get this for all. Let us delete all this value. So now I have in each bin what is the corresponding frequency. Then we can basically plot the histogram. So let us plot the histogram. So on the x-axis basically we can plot the either lower bin or upper bin. So we can also plot the mean of the bin, or we can also plot both lower. So let's just change this, and on the x-axis we are plotting the lower bin sizes. So here I have to edit this, and this is the lower bin. So now this is the lower bin. So you see, no, there is a mistake. So this is the lower bin. I have to change only this data. So on the x-axis we have the bin interval, on the y-axis we have frequency. So from here we can basically calculate what are the corresponding frequency of profit. So on the y-axis we have profit. So here we have profit. On the x-axis basically we have win. So frequency of profit. So this is frequency. So we can call this as a frequency. So this is the second part. We have to basically plot a histogram corresponding to the total profit. In the next part of the question it says we can basically calculate what are the corresponding sample statistics. So using the result of, so we have to perform this analysis for 100 samples. So we perform for 100 samples. Using the result from the Monte-Carlo simulation, estimate the probability of loss for a given year. So let's find how many terms we have negative. That will give me the positive. That will give me the basically loss. So we can find loss simply by finding how many total number of negative term we have. So loss we can find, this is equals to, if we can count, so let's say count if function we can use again. And then we have to give range, and in this range we have to simply look for negative value. So if something is less than equals to 0 or simply less than 0, so this is loss. So there are only one term that is negative. So let me see. So this will go up to 110. So this is 1. Yeah. So there is only one term that is negative. So if you see from here, so this term is negative and none of the other term is negative. So this simulation says out of 100 only one sample is negative. So percentage loss will be 1 by 100. So I can also calculate percentage loss. This is equals to this number and divided by 100. So this is equals to this divided by 100. So you see one important point, I can basically I have to also multiply by 100. That will give me the percentage loss. So this is around 4%. So you see each time when we are using this number keeps changing. So in Excel basically this simulated sample keeps changing. What you have to do is you have to put this cursor in any cell and press the F2 button. So if you press F2 and then put this number will change. So each time basically this is simulating different sample, and in each case you are getting different percentage loss. So if you increase this number of sample, basically you will converge to a literally more accurate result or more concise result. In all cases you will have same. For this case we can also calculate what is the corresponding mean, what is the corresponding standard deviation, and different percentile values we can also calculate. For example, we can calculate what is the mean of R, that is total profit. So we can calculate mean of total profit. So this is equals to average, this is equals to average of this will go up to 110. So this gives me the mean of profit. So this is 45,189. Similarly we can calculate a standard deviation, and this is equals to STD-def, and this goes from 110. So this gives me mean and this gives me the standard deviation value. So we can calculate corresponding other percentile values also. So this is all about the Monte-Carlo simulation. So to summarize what we said in this class, basically we said there are 4 steps by which we can simulate Monte-Carlo simulation, and in the first step you have to simulate a random number, and then using that random number you have to use inverse transformation, and in those cases you have to simulate a corresponding input value. And once you have the input value for all the random samples, in the third step you have to basically use the model deterministically to solve for those input value. And once you have this one sample, you have to repeat from 1 to 3 step, and you have to basically generate multiple samples, and finally you have to plot a histogram of the data of the y value of the output value, and this is the output value for 100 trials. So what we have said, we have used 100 trials, and there is a profit and there is a relative frequency, and we calculated mean, variance, standard deviation. We can also calculate coefficient of variation. So using this we can basically see what is the mean value, what is the variance value of profit, and we can get some idea from this kind of simulation. This simulation is just an illustration. Using 100 trials we can increase the number of trials, and we will see in the next lecture how the number of trials can affect the result. So how many trials we should need and how we can affect the result based upon the number of trials, accuracy of the result. This we'll discuss in the next class. For this class we can basically stop here. In summary, we have different trials. For each trials we simulated a random number, and using this random number, so for this is for income, we simulated using norm inverse PDF in Excel sheet, this normally distributed random samples. For exponential distribution we have these random numbers using the formula that we derived in this class, analytical formula. We basically simulated exponential numbers, and then we calculated the profit, and this case we can basically plot the histogram of the profit, and then we can use this histogram or the data that we have simulated to calculate the sample statics. So this is all about the Monte Carlo simulation. This is a very powerful technique. Even though we have illustrated with a simple example, this can be basically used for any case of model, and I will suggest you use this kind of simulation example in your project COVID data set. So use some simulation, you assume some kind of random variable distribution, and then try to do some simulation. Then you will get idea how this can be implemented or how this can be applied in real life situation. Okay, thank you so much.